Yeah, thank you so much. So my name is Phillip Weinberg. I am a senior scientific software engineer at QueRa Computing, and it's my pleasure today to give you guys a tour of our new and improved SDK, Bloqade. So roughly, what I'm going to talk about today are the two major components that we've added in the past year. We're going to talk about why, and in this case, as we move from the analog to digital regime, we need a new software stack in order to handle that change to our hardware. Yes, so going to talk about our circuit library, Bloqade Bloqade circuit, along with our new SDK for defining atom shuttling, Bloqade shuttle. And then finally, I'd like to talk to you about how you can partner with QueRa to develop your applications and access our hardware. Yes, okay. So as I mentioned before, QueRa started out as an analog quantum computing company. We heard a talk about Aquila earlier today. And as such, we had an SDK related to programming that device. But now we're moving towards a digital version of our machines, and so we need a new software stack to accomplish the goal of executing the hardware in the most efficient way possible. So what I'm going to talk to you today about are two SDKs. One, a high-level circuit SDK, which I think may be more familiar to all of you. This is called Bloqade Circuit. The idea behind Bloqade Circuit is not necessarily to provide the idea is we want to try and provide a solid entry point for users to program, as well as an entry point into our compiler stack as well. The key point here is that the SDKs that we're going to talk about today are specifically oriented towards neutral atom hardware. They're also embedded in Python. This is in order to make sure that you're able to work with your existing Python workflows, whether it's through Qiskit or Circ or some other SDK. So if you're programming in Bloqade Circuit, what will happen is when you actually want to lower to the hardware, you're going to be lowering to another IR and SDK called Bloqade Shuttle. And what this is doing is this showing you an animation of what kind of code or how you can actually program the machine. These are simulated atoms inside the quantum processor, along with flashes representing gate operations. So on the shuttle level, you have control over exactly when these atoms move, where do they move to, so on and so forth. And then from there, we can lower that lower level program down to our hardware level representation. In this case, you can think about pulses, and I won't talk about that today. However, just keep in mind that down the stack, this will be further lowered to something that is more compatible to our quantum operating system. All right, and another key point I'd like to talk about is advertise is all of this stuff was built with our new compiler toolchain, which you have heard mentioned in a few previous talks, called Kirin. So before we go on to talk about the SDKs, I'm going to just give you a brief overview of what Kirin is and how it could be useful for your software development. So Kirin is a compiler toolchain, which allows you to define embedded DSLs that are embedded inside of Python. The idea is you can build a semantic, and then you can use that to program something inside of a Python function. The idea is to basically build up a bunch of small pieces, much like in the MLIR fashion, to build a set of semantics which allows you to iterate and, it provides a way of sharing a common set of semantics that you can use across different compiler tool chains. In this case, some of the main features I would like to advertise for Kirin is that You have the ability to define your dialect, and it also allows you to directly integrate inside of Python. So you get basically this lowering from the Python AST down to the Kirin's built-in SSA-IR. This SSA-IR is inspired by MLIR, and it's also universal. So both the Bloqade Circuit SDK as well as Bloqade Shuttle are going to be using the exact same compiler toolchain, the exact same AR, which allows you to flexibly switch between both circuit and a lower level representation. Some other key features are abstract interpretation, which is used for data flow analysis. So for people coming from compilers, there's basically a way of formulating static analysis of a user's program in strongly typed systems. And the abstract interpreter is allowing us to basically handle more complicated type systems that are defined inside of Python, which is a dynamic programming language. There's also tools to interpret the IR, which is useful for debugging, which I'll talk about later today in the two different presentations about the subcomponents. And then we also have optimization as well as code generation to generate, let's say, non-Kirin-based intermediate representation. Okay. We're moving away from analog mode. That doesn't mean that we're not going to support analog mode. So just for reference of anyone who is using Bloqade, we have renamed Bloqade to Bloqade Analog, and we will be supporting it as long as we are supporting our neutral atom analog processor. So just a bit of housekeeping before we continue. Okay, so now on to the fun stuff. So Bloqade Circuit is our circuit level SDK, and one of the key components that we heard about earlier today was the idea of having more structured quantum circuits. In this case, we've actually named the intermediate representation defined inside of Bloqade Circuit as SQUIN. The idea being we have quantum instructions mixed with structured control flow and other programming concepts, like closures, functions, and I'll get into a bit more detail about that later on. We also want to make sure that you can integrate with our compiler, not necessarily through our SDK, but through other SDKs. So we have implemented a CHASM2 integration, so you can directly lower from CHASM2 program down to our SQUIN language. We also have integration with Circ, and then we're in the process of actually integrating with QuEra. So once you've entered the compiler pipeline, you can either go downstream where we want to actually program and execute instructions on the hardware or at the shuttle level. We also have a IR interpreter, so basically a built-in simulator. So if you just call a function, it will call the simulator based on PyQuEra. It's a unitary fund project, which we have used to fairly heavily in our simulations. And then another thing that we are working on actively is integration with STIM. So if you're interested in error correction, you can take your SQUIN kernel in this structured way and actually generate an equivalent STIM program. So on top of some basic QEC primitives, which you can define, this provides a nice tool chain for you to think about and simulate quantum error correction. Okay. So what does a SQUIN program look like? So in Python, we have what we call our decorator, you call it in Python a decorator. So what you have is you have a Python function with Python syntax that you're decorating with a basically a tool that comes out of Kirin. And what this will do is it will take this program and it will lower it into SSA-IR. In this case, I'm going to show what happens when you print out the IR directly. It's not particularly nice to look at. However, I've spent many hours debugging my compiler, or our compiler at QuEra in this format. I just want to point out that the IR is this SSA form. You've got these SSA variables which are assigned statically. And the structured part of SQuIN is this structured control flow. So if you are familiar with MLIR, this will probably look somewhat familiar to you. The idea is I can take the block of code that lives inside of this for loop and nest it inside of this region here, which allows us to better encapsulate what the user is actually writing in their program. The other thing that we are trying to include in terms of the structure of the syntax is we're a neutral atom quantum computing company, and as such, the platform itself is highly parallelizable. So we want parallelism to be a first-class citizen in terms of the not just the IR, but also the syntax that you use. So we have a set of basically, you can think about it like SIMD instructions, where I can take a gate, let's say an X gate, and broadcast it over a sequence of qubits. We also have noise that you can embed directly in your program if you'd like. And also we have tools which allows you to automatically insert these noise statements inside your program with heuristics that will try to mimic how accurate or mimic how good the move synthesizer would be when you actually lower this down to Bloqade shuttle. So yeah, if you're interested in learning more about Bloqade and Bloqade circuits, you can go to our documentation page here, bloqade.QuEra.com. There's a lot of stuff that you can read. There's examples and tutorials on how to use Bloqade circuit and SQuIN in particular, along with some background material about neutral atom quantum computing. In the roadmap, so what we're actually doing at the end of 2025 and into 2026. So one of the things that we found is that our original representation, while very flexible, was more difficult to compile, and as such, we are going back and simplifying our existing compiler IR to be a bit more simple. If you're interested in the discussion, you can check out this PR number 492 on the Bloqade circuits GitHub page. The other thing that is on our roadmap is we want to integrate with CUDA-Q and QIR. This is very important for getting the best performance out of GPU-accelerated devices for simulation. And we're also working on improving our STIM code generation. In this case, one of the key things we'd like to try and do is try and compile for loops in SQuIN down to repeat statements inside of a STIM circuit. And then, of course, as we are improving the IR, this is also helping in improving our compiler stability. So in this case, less bugs, hopefully, going forward as we simplify the IR directly. Okay. So now I would like to talk a bit about one of the projects that I have worked on fairly significantly in the past 6 months. This is Bloqade shuttle. So the way to think about Bloqade shuttle is it's a small, well, not small. It's an SDK which allows you to define very low-level hardware operations and package them together to form concepts that are similar to gates. So inside of a neutral atom processor, there are optical tweezers which pick up atoms and move them around the two-dimensional plane as you are trying to execute different instructions on a neutral atom quantum computer. So for example, some of the actions that you might include here are, I want to set the position of the traps. I want to turn on some of the traps at particular locations. And then there's going to be a sequence of moves. And then maybe turn on some more traps. So you have a very high amount of flexibility in terms of writing individual operations on optical tweezers. And then the idea is you want to package this into its own separate kernel, because what we want to do is we want to try and build an abstraction for a move that you would do on the hardware, and this brings it to the level of effectively on the level of a gate. So I have my So I have my kernel here, and what I'm going to do is I'm going to tell the compiler I want to execute this kernel with a particular set of hardware resources. So one of the things that you'll see in here is that grid comes up quite a bit, along with this immutable list. So immutable list is just a list of values, in this case just a list of integers, which are corresponding to the indices inside the grid that I'm going to try and attempt to move. In this case, I'm going to move into the gate zone. But the way that you actually define the positions of the atoms is using a grid object. And the reason for a grid is that that is right now how you actually think about the configuration of the optical tweezers. So we provide a lot of support for manipulating this grid, whether it's slicing, indexing, shifting, scaling, lots of different things that you might want to do to define the path in which the atoms take during the execution of a move itself. We also have visualization tools. Another very important part of the toolchain is to be able to debug these tweezer kernels. So here's an example of a still frame showing what exactly this kernel would be doing in a particular call. So in this case, I am going to pick up these two pairs of atoms here, and I'm going to rearrange the traps and then pick up these four atoms here. So here the dots represent the atoms, and the arrows are representing the different moves. So you can see here there's 1, 2, 3, 4 moves. So you have 1, 2, 3, 4 arrows. So each arrow corresponds to one of these move commands. And then as you go, if you turn on and off the different traps, you'll see that these arrows become dashed to solid. The red band here represents basically the CZ pulse. So this is basically a laser that will shine in this particular region in order to do a CZ gate on these atoms that I have moved inside of this patch. Yes. So now that I've defined my entanglement move, in this case I'm going to do a move to entangle the qubits, or the atoms in this case, I need to assign it some resources. And so in this case, there's not super important, however, the amount of, there's a thing called tones, not super important here, but roughly speaking, the size of the grid corresponds to the number of tones inside the tweezer. So in this case, I assign the device function, or I assign the move function to a device, and then I define a reverse of that move. And the idea here is I want to run a C0 gate. So I first start out by doing a local gate. So I'm going to shine a local laser pulse on a subset of my grid, in this case, the memory zone, at the first argument QArgs. Then I'm going to move the atoms to the gate zone using the move function that I defined earlier. Then I'm going to apply the top hat, which is what this red band is called, top hat CZ gate in the gate zone. And then I'm going to call the reverse task, which will effectively take what you just did and do the exact opposite. And then after that, I'm going to finish up the gate by doing basically the opposite pulse. So this is going to give us basically the CX operation. Okay, so that's kind of, and a very quick explanation what exactly Bloqade Shuttle is. So you might ask, why would we want to have this? So the idea here is we want to provide a platform for users to experiment with different ways of thinking about neutral atom architecture and the primitives that you would use to actually define the actual moves inside the architecture. So in this case, I defined a line, and then I defined a move kernel, which would basically account for the fact that I only have static traps in this region, as well as kind of a top hat in this region. And all of this stuff is completely configurable. You can actually specify where the top hats will be, where the static traps will be, and you can combine that with your moves kernels, and this allows you to basically model exactly what a quantum device would do. This is very useful because you want to understand the noise characterization of your moves. So this encapsulation basically allows us to figure out, okay, given a particular kind of move that you're trying to operate, what is the rough estimate of what this noise would look like for a particular move. We also have gate operations as well. The gate operations are a bit simpler. But the nice thing is that at this point now, gates and moves are effectively on the same level. So the encapsulation allows us to capture the error due to moves alongside with gates, gives us a very low-level representation of the noise character of the machine that you have, in principle, built. So this is useful because if you're starting out from Squin and you want to borrow one of our architectures that we've implemented inside of the library, what we can do is we can basically take your Squin circuit, we can compile it down to this move architecture, and you'll get nice animations like this. This is useful for debugging the compiler. So here's an example of where I do a GHZ state using this move kernel on multiple pairs of atoms in a log depth fashion. So from here, yes, animation you can use to debug. You can also use to model the noise. And this, from now, once you are fairly confident that your architecture and your compiler are working, you can then lower this down to hardware signals. So one of the key things that we're trying to do, and why I'm actually here at this conference, is I am interested in getting feedback basically from anyone who's working on neutral atom compilers. We want to try and come up with a way of representing these atom move semantics such that we can hit multiple, both private and academic move synthesizers. So in this case, one example is our this ZAC, so-called zone-aware compiler out of a group at UCLA. And so we've been working with them to try and understand exactly what does their compiler do, how exactly we can basically get a unified IR that will allow us to integrate multiple neutral atom compilers. Another important milestone would be to, after we've converged on the IR, we want to try and automate the moves. So part of this is handled by these compilers, but there's also, when we have multiple devices, we want to be able to automate how these moves are assigned to devices and executed in time. And then finally, we're interested in building out, so we've got this IR, we want to be able to build the emulation capabilities like I talked about before, this animation, and other common tools. So for example, if I want to know roughly how the fidelity of the execution of this program, that would be useful for anybody who is targeting this IR with a compiler. But there's also things like atom position analysis to make sure that you're not actually having atoms collide. So this is a very low-level control. And also, yes. Okay. So some of the ways that would be we would like to reach out to the community to partner with us. These are both open source packages, so feel free to download them via pip. In this case, Bloqade-circuit is how you would install Bloqade circuit, and Bloqade-shuttle is how you'd install Bloqade shuttle. We're really interested in understanding how people want to use neutral atom hardware. So if you're interested in neutral atoms and you want to try and write your application, we would very much encourage you to try and use our specific syntax with the structured control flow like for loops, if statements, as well as the parallelization. So for example, one exercise I wanted to try and write was to take the GHZ state prep, log depth GHZ state prep, and actually come up with computation of the different numbers of layers on the fly as you're executing the code. If you're interested in accessing QuEra's neutral atom hardware, this is also a very useful place to start. As mentioned before, we're working on different IRs to support integration into the compiler pipeline. So if you have an issue with either CASM or QIR, we can help you integrate directly into our compiler stack via Squin. For Bloqade Shuttle, as I mentioned before, I'm very much so interested in working with compiler developers. We want to try and come up with a common set of semantics to process and represent atom shuttling for neutral atoms. Also, if you are interested in, as a corollary to that, we want to try and use that representation to target our hardware. We want to make sure that your applications that you're writing can give the best performance possible. And then finally, if you are interested in learning more about the nitty-gritty details about how neutral atom compilers work, I think Bloqade Shuttle is an incredibly useful place to start. You have concepts like the optical tweezers and how they work, how they interact with the hardware via the assignment of tones. These sort of things are very useful, and one can help you learn about neutral atoms and write more optimized applications. So yeah, as mentioned before, we have open source, not just Bloqade Shuttle and Bloqade Circuit, but also Kirin as well. So if you're interested in talking with us directly, we have a monthly Bloqade community meeting. There's a registration link that you can find here. And of course, like any other open source package, we welcome contributions directly to our repo. In this case, documentation edits are incredibly useful. Feature requests are also very useful. And if you're really in the weeds, bug reports and pull requests are always welcome. So yeah, and also finally, yeah, star us if you find Bloqade is interesting or useful to your project. That really helps us out. So yeah, basically that's all I have to say today. Stay tuned for additional open source packages. Thank you so much. Open the floor to questions.
Thank you, Philip.